Hi, so now I'm back in the lab for a third video about the Geiger counter. In the first video I gave you an example on how one can listen to a Geiger counter and learn about decay statistics and how this challenges our worldview about possible determinism. In the second video I discussed more about how the Geiger counter works and how it detects radiation and why it is called a counter, not a spectrometer. Now in this third video we're going to check how we can shield different radiation types, which tells us more about the properties of alpha, beta and gamma radiation. So let's start. Okay, so this is the setup we're using now. The Geiger tube here, the gas field detector, there's the entrance window, and this time I have from the start removed this protective cap so that the alpha radiation can penetrate easily, so that the sensitive volume starts somewhere roughly here, and then it extends for a couple of centimeters. And I have my holder here, and then I provide this with high voltage from this box here. It should be set to 500 volts. It's not so easy to set it exactly, so it will vary a little bit, plus minus a volt or something like that. But this is not so important for this little experiment. And then I have my radiation sources here, an alpha source and a gamma beta source that we're going to use. And I have different kinds of shielding material. And towards the end, I think we'll also try to vary the distance and see the law of distance, how this affects the count rate. So right now I have switched off the sound, so it's not too disturbing, but we'll start that soon. Now let's switch to count for a period of 10 seconds each time, and I switch now on this the sound. Now we hear the first one, and then if I press start, we will collect the background counts for like 10 seconds. Let's see, and when this is ready, it will start blinking. How many background counts do we have? 12 counts in 10 seconds. Let's make a second measurement. Oops, obviously I didn't press properly. Now let's see. So where do we end up now? 8, so it varies a little bit. This is also statistics. It's a very low counts, on the order of 1 count per second in background radiation, and that's maybe what you can hear just by listening again to the sound. So then let us start with the americium source. So this is americium 241. So this is something that undergoes alpha decay. And in the process of that, also a little bit of very low energy gamma rays. It's on the order of below 100 keV. And I go very close to the entrance here, and you can hear that the count rate has gone up dramatically. If we remove it a little bit, it does not have a large influence unless we get at some point here where it suddenly drops almost to the background level. If I go a little bit further, let's see, and I reset this and see how many counts that is. It's above the background level. Mind you, that is also gamma radiation coming from there. It's 40 counts. It's not a huge increase. So still around, let's see, close to 40 counts. So it's 4 times above background. But if I go closer, just like this, for example, then we have an enormous increase in the number of counts. So where do we end up in that case? 1800. Let's redo, verify. about the same, a bit higher. We can go a little bit closer. Will not matter a lot. I think maybe a bit higher because of geometric effects, because just we're closer. Ah, well, okay, more than I thought. 3100. Let's get even still a bit closer. Let's see. Okay, 3600 counts, and which is a drastic difference to what we had here. So what this demonstrates is that air already is shielding the alpha particles. So next we're going back. I will move it very close, and we start with the shielding experiment. I leave a little gap here, and first, yeah, let's repeat to be sure that we have a good comparison, not just listening, but really looking at how many counts we have. As you've seen, it's still quite sensitive to the distance, close to 3,400 counts. And now I just put a piece of paper in between. So it's an ordinary piece of paper that I took from the printer. And let's see. We're down to about 60 counts. So this is probably mostly the remaining gamma radiation from the source. So all the alpha particles have been absorbed by this piece of paper. So alpha particles are so densely ionizing that they lose so much energy already in a thin piece of paper that they don't make it anymore into the detector. And that tells you also something about how thin this entrance window, this quartz window, must be in the detector in order to get any alpha particles inside at all. And of course, if I use something thicker like this cardboard, we will have sort of the same effect, maybe shield a little bit more of any remaining gamma radiation. See where we are. 30 counts. So essentially we shielded the radiation from the source. So it's quite easy to shield. So what that means, and that what I tell people all the time, yeah, alpha radiation, if you have an alpha source over there, if I stand far enough away, then it does not give any harm to me, any harmful dose. On the other hand, it means if I would, for some reason, swallow that source, then the damage that I would get into my organs or so, or for example my lungs or so, could be quite high because of this, because of the high ionizing density. And that is connected to the problem of radon, which leads to alpha decay in your lungs and so on. So, okay, so that much about alphas and the americium source. So let's switch and take this other source here. This is cesium-137, and that emits beta and gamma radiation. So this is decay of cesium-137 to barium-137. That is a beta decay, so that emits a beta particle and an antineutrino. The antineutrino is not doesn't interact. It's very unlikely to interact, so it's very penetrative. So we're not measuring that one, but we can register the beta particles. And then in most of the decays, the daughter nucleus, the barium-137, is still in an excited state, and this will decay to the ground state by emitting gamma radiation. So it's both beta and gamma radiation that comes from that source in roughly the same proportions. So if I switch on the buzzer for a while, just for dramatic reasons, let's say, after a while it's quite annoying to have that in the background and so on. We have a very high rate now again. Let's count how many we have. And I've left a little bit more distance, so I can add a little bit of more shielding. So that source gives us almost 5,000 counts. Let's see, second measurement, verify, 4,759. And yeah, okay, let's try with this piece of paper again. And as you can hear and as you can see, when you look at the number of counts that we end up with now, it is practically no difference. So this piece of paper, well, okay, a little bit of gamma beta radiation, but it is a very small difference compared to the earlier dramatic effect of the alpha particles. Let's try again. Okay, close to 4,000 counts, so a slight decrease. So it would be a larger increase, of course, if I take this cardboard. Let's see. You can already hear. But it's by far not the same drastic decrease as we had in the case of the alpha particles. Now we're up down to, like, what is it, 562. I'm trying to read that upside down. It's a bit confusing. Verifying measurement. 10 seconds counts to, what do we get? 569. Is it correct? Yes. Okay, so and if I remove that, and now we have a piece of aluminium, and that's about 1.3 centimeters. Let's see. Oh, I miscalculated a little bit. I have to go a bit further back, which will of course influence our statistics a little bit. Let's see, and I put it like that and as close as possible. And let's count. And we're down to, let's see, that was 49. And verification now. Yeah, 57. Okay, well, big variance here. And let's see once more. Oops, we're increasing. How come that? 76. Let's check once more. Okay, we have low counts, so there's a large spread in the number of counts that you get. So it varies between, yeah, just below 60 to over 70. So it's 60 plus counts, it seems, on average. Of course, we can increase the collection time and get a better statistic in just one measurement. But somewhere between 6 and 7 counts per second, it seems to be. So it's still above background. It's not completely shielded. Yeah, essentially we have removed the radiation. So as a last thing, well, okay, maybe let's briefly summarize. You saw that there's quite a difference between this alpha source and how easy it is to shield. So that's also a way to check what kind of source one has, and the gamma beta source. What I now would like to do in this final example is record the number of counts in a certain time period as a function of the distance, and for that I have a ruler here, and then maybe as some kind of a homework exercise you can draw this curve, how many counts we have in a 10 seconds period as a function of the distance we're going to measure here. And then mind you that there's a volume. What I will measure is the front of the detector, the sensitive volume. The average impact pound will be somewhere behind the entrance window, but I don't know exactly the dimension, so I will measure to the front, so there will be some offset in your graph, but maybe you can find then out how far it penetrates into the detector. So it's just going to measure here the distance, and right now, let's see, I will set it to, this is, yeah, 2.5 centimeters. Maybe I have to go a little bit further back here. try to do it as good as possible, but just by eye. It's not very exact, but now I have 2.5 centimeters difference between the front of the source here. But again, here it's the same thing. The source is not exactly at the front; it's slightly further in. And again, the detector, it does not start at the front cap, but a little bit further back. So there is a bit of an offset, additional offset. So mind you when you draw that in some when you make a graph in some program or drawing on paper. But okay, now we have 2.5 centimeters difference, and I switch on again the buzzer here. Let's see, and we measure for 10 seconds. Okay, 3009 counts. Let's verify with a second measurement that it is reasonably stable around that rate. Okay, so this is our second measurement. So because this is quite high counted, I switch off the buzzer for a while I put the distance, I increase the distance and I put it at 5 centimeters, so I double the distance, or yeah, something like close to double. Again, mind you about the offset that we have. So now I measure 5 centimeters between here and here. Okay, for the measurement, again, let's switch on the buzzer. But of course I don't need a buzzer, it's just to have the additional audible verification. So for the second measurement, let's switch it off. So now we have almost 1300 counts, and the verification measurement, now we are at, let's see, slightly above 1200 counts, so very, very close to the same result. And for the third measurement, and after that we will leave it, we go to 10 centimeters. Let's see now. So this is, yes, 10 centimeters distance, and I let the buzzer off this time, and you will see we'll get a lower count rate. What is it, 51. Second measurement, a bit more. So mind you, this is alpha, gamma and beta radiation that we have here. We have changed the distance twice, so we have 3 different measurements. And maybe also, just to be sure, we can repeat also the background measurement. I remove the source here, make one background measurement. Let's see whether it's sort of the same as before. We had like 1 count per second. Now it's half a count per second. Let's repeat it. Yeah, okay, it's statistics, sometimes a bit higher, sometimes a bit lower. Just to be sure, let's make a third measurement. Okay, this time was very low. Let's make a fourth one. Let's see where we end up that time. Of course, you could average that out, but in comparison to the high rates that we had in the other measurement, this is almost negligible, so you don't necessarily need to subtract it. So all were very, very low, between 4 and what was it, I think 18 or so counts in 10 seconds. Okay, and what this means is, of course, not that the activity of the source changes, just the distance changes. That means fewer particles that are emitted from the source really hit the volume or hit the entrance of the detector and are registered. So I'll leave you that is a little homework. Try to make a drawing and see if you get the correct law of distance. Thank you for listening, and thank you for watching.